Hello from Intellipaat, guys. The topic for today is Hadoop ecosystem. But before we begin, be sure to hit that subscribe button and click on that bell notification icon so you don't miss out on any updates from us. So for the agenda today, we have the Hadoop ecosystem and the Hadoop ecosystem components, some of the main components we're going to be discussing today. After that, we're going to be having a look at the HDFS architecture and the MapReduce workflow. And we're going to be doing a little bit of hands-on today with the MapReduce and Hive tutorial. So without any further ado, let us begin. So the Hadoop ecosystem. So basically, we have all of these components that are present within our Hadoop environment. So it starts off with the HDFS, which is the primary base for all of the Hadoop functionalities. This is the storage system. This is the distributed storage system that we use for Hadoop. On top of Hadoop HDFS, we have our Hadoop Yarn, which is the resource management implementation inside our Hadoop environment. So on top of Yarn and HDFS, we have all of these frameworks and libraries and applications. We have Spark, we have MapReduce, Hive, Pig, HBase, Zookeeper, Uzi, and all of these things. So we're going to be discussing some of these in detail when we begin with our components of the Hadoop ecosystem part. And as we can see also at the bottom, we have our Flume and Scoop. So these are some of the bridges that we use in order to transfer data to and fro from various web applications or relational database management systems to and fro from HDFS to that. So let us begin with some of these components. Let us just get into these. So Hadoop ecosystem components. Firstly, we have the base thing, the base implementation of our Hadoop ecosystem, without which any of this is impossible, the HDFS. So HDFS is also called the Hadoop Distributed File System. It is the abbreviation for that. So as we can see in the definition here, HDFS is a file system designed for storing very large files with streaming data access patterns running on clusters of commodity hardware. So one of the things that was present in traditional databases where distributed databases where we were dealing with distributed file systems to store big data, we didn't have a system which was robust and efficient, and we were using very expensive hardware to store this information. So with the introduction of the HDFS, it allows us to use commodity hardware in order to store our big data. So what does commodity hardware mean? Commodity hardware basically means that we can use basic office level equipment. We don't need to buy any special hard drives or server systems in order to store our data. We can use our computers present inside of the office and dedicate some portion of that computer's hardware resources to our Hadoop cluster. So that is why it significantly reduces the cost of maintaining a distributed file system in order to deal with big data problems, and basically helps us also with an implementation of data replication so that we can basically copy our data and save it from being eradicated in the event of any hardware malfunction or whatnot. So it is used to store very large files and for streaming data access. And the main advantage of the HDFS is the ability to use commodity hardware to run it. So then we have MapReduce. So this is the processing element of the Hadoop environment. So it is the core component of the Hadoop ecosystem as it facilitates the logic of processing. It is a software framework. It is a purely software framework, while we can say that the HDFS is something that uses the hardware in order to simulate a distributed file system by connecting all of these hardwares together to create our distributed file system. MapReduce is purely a software framework, and it helps us execute the algorithms or the code that we push into our HDFS, that we push into our Hadoop ecosystem in a parallel format. So whenever we execute things in parallel, it divides the time by half. So if we're executing a program in parallel that has two components, it basically reduces the time that it would take to execute that program in half. So MapReduce plays a very crucial role in the Hadoop ecosystem, and it uses multiple machines in order to solve a single problem. So MapReduce is basically comprised of the map function and the reduce function, and we're going to be discussing this in detail when we reach our MapReduce workflow part of our session here today. So after that we have yarn. So all of these things are very much implemented like HDFS and MapReduce, but in order to run jobs, in order to be able to allocate resources to our jobs that we would ask our Hadoop ecosystem to execute, we need a resource management program, right? Because we need to basically assign the resources that are present inside our vast Hadoop cluster to the jobs that we want to allocate resources to. So yarn, which is the abbreviation for yet another resource negotiator, it is basically composed of two parts, the node manager and the resource manager. So the node manager is present to purely manage all of the resources, to purely monitor all of the resources that are present at a node level. So it basically helps us keep track of the current resource situation and the resource management implications of all of the nodes that are present within our cluster. And the resource manager helps us when a job comes up, when we have to execute a queued up job. So the resource manager helps us to allocate resources to that particular job. So that is the functionality of yarn. So yarn is not just only used by the MapReduce functionality, it's also used by Hive, Pig, and Spark as well. So after yarn, we can now talk about Scoop. So Scoop is fairly a simple application. So it's not built on top of our HDFS. It's basically a connector bridge between a traditional database management system and our HDFS. So say that we have a Oracle server which houses a database, and we need to transport this database. We need to transfer this data that is present within that database to and fro from our HDFS, which is our Hadoop distributed file system, to our RDBMS, which is our Oracle database. So we can transfer data to and fro using the bridge we call as Scoop. We basically connect these two applications like our HDFS and this RDBMS, and we can transfer data to and fro. So exporting and importing tables basically. And then we have Hive. So like any data warehousing tool, Hive is also a data warehousing tool. But the catch about Hive is that Hive is a data warehousing tool that is supposed to act on top of a Hadoop cluster. So that data which is present inside of inside of the HDFS, Hive can essentially take that data and warehouse it so that we can perform some queries on it, and we can write some user-defined functions for that particular data that we have just warehoused with our Hive, and gather some information, gather some insights out of that data. So the primary functionality of Hive is converting a semi-structured or unstructured data formats into structured data formats, so that we can basically query it with an SQL-like language which we call as HiveQL. So Hive is used for data extraction, and it is also used for data querying as well. So Hive also uses the MapReduce functionality in order to run its queries and jobs with a much higher speed and efficiency. So after that we can discuss Pig. So Pig is kind of similar in a way too, but it's an ETL tool which is extract, load, and transform. So Pig is basically a way for us to execute very complex programs in just 5 or 6 lines of code. So as we can see in the third point over here, Pig Latin is a specialized high-level language. A high-level language basically means that we don't need to know coding as much. We don't need to know any sort of particular syntax in order to execute our Pig statements. It is a high-level language, which means it is understandable by a simple user who doesn't even understand coding. He would understand what a simple statement is, and then he could use that high-level language, which is called Pig Latin, to execute complex program functionalities. So as we can see, one line of Pig Latin code would constitute for 80 to 100 lines of code in a traditional MapReduce Java program. So that is kind of the advantage of Apache Pig, to reduce the LOC, which is another abbreviation for lines of code. So we can run Apache Pig in either a MapReduce mode or the local mode. So in the local mode, it would use our local file system, while in the MapReduce mode, it would use our HDFS and basically run a mapper and reducer on it. So after that, we can now discuss Spark. So Spark is the most popular tool, the most popular framework that we use for big data analysis today. And the reason for it is because it is the most modern and the most up-to-date with the current times. So as hardware costs have gone down, Spark has become more popular because it uses in-memory processing. So what does in-memory processing mean? It means that we transfer the data into our physical memory, aka RAM, and after that we can basically execute and process and query that data with almost zero latency because it is present within our RAM, because we are caching that and we are actually adding that data into our RAM. So whenever we are creating an RDD or a data frame out of a particular data that might be present inside of our HDFS, we're basically transferring that data into our physical memory. So compared to the HDFS, compared to our traditional MapReduce applications, Apache Spark is about 100 times faster when we are actually performing tasks by loading data into memory. So it is also used for real-time data analytics just for that reason as well, because we can import data periodically into our HDFS or any distributed file system, and Apache Spark can process that data in real time because it is just that fast. So we can integrate Apache Spark with Hive using Hive context. So we can basically implement Hive tables with Apache Spark. We can import Hive tables as Spark data frames, and we can run our data frame queries on it. Apache Spark also has libraries / APIs for Java, Scala, Python, and R. So basically, using the Apache Spark libraries present for these programming languages, we can just have the expertise in these particular languages and execute it in a way where we don't have to learn anything new. We just have to execute Java, Scala, Python, and our programming logic, and we can basically implement our coding logic with it and implement our big data functionalities with it. And then after that, we have simple SQL queries. So if you're well acquainted with SQL, you wouldn't have an issue dealing with Spark data frames. So let's go head on to Flume. So Flume is basically a data ingestion tool. We basically ingest structured and unstructured data into the HDFS. So how does that work? So say if you have a Twitter application, if you have a Twitter web application, you can basically create a developer account for Twitter and create an entry point into your HDFS from that Twitter developer account and ingest some Twitter log data or Twitter web application data into your HDFS. Now this data can be really large in nature, depending on how much data you're actually ingesting. So you can basically ingest that into your HDFS, and then after you've ingested it into a particular directory, you can use any of the other HDFS components or your Hadoop ecosystem components to take that data and process it, run queries on it, and whatnot. So as we can see in the diagram, in the cloud icon, we have our web server, and that is giving a data to a source. Now that source is basically channeling that data through a particular channel, and that is syncing into our HDFS with the use of the entire agent, the Flume agent as we like to call it, which is the technical terminology for it. So these were some of the day-to-day used components for our Hadoop ecosystem. So now we move on to the HDFS architecture, because it is pretty important to understand the HDFS architecture before we actually understand how Hadoop works. So as we can see, we have two components primarily, the name node and the data node. So in short, the name node basically contains all of the metadata, and the data node contains the actual data that is present within our HDFS. So basically files are divided into multiple parts, which we call as blocks. So the name node would contain the pointers to these blocks, to the starting points of these blocks in the memory, and basically contain all of the information as to where these data blocks have been replicated. So all of this metadata is contained within the name node, and the actual data is contained within the data node. So if we actually look at the process of how data is written into the HDFS, just to get a good idea of how this works. So first step is the client requests to create a file, and the name node is contacted upon this request that, okay, the client wants to basically write a file into the HDFS cluster. So the name node is contacted. Once the block of data is accumulated, once the block of data is transferred by the client. So the name node responds with a list of data nodes to basically imply where the client can store the data that it is requesting to store, as to basically imply which data nodes are free at the moment and which data nodes have space at the moment. So once the data node receives the data from the HDFS client, the data node forwards this particular file to the second data node and the third data node, depending on the replication factor that is present in that HDFS configuration. So after the data has been replicated, we are now safe from hardware failure. So in the case of any hardware failure, we basically have a fail-safe and that data is copied, so we are not going to lose that data. So after that, the name node commits the file creation into persistent store. Basically, name node stores the metadata for that particular commitment of the data into the data node, and it keeps checking for heartbeats and block reports. What does that mean? It keeps checking that the data nodes are functioning in order to maintain a statistic of whether the data nodes are healthy or not. So in the case of one data node going to failure, it would basically replicate that data block once more into another data node, so that there are still two more replicas of that data. And that is basically the point of it. So the client gets the data node list from the name node, and it reads that particular replica closest to the render. So say that if you want to read that particular data, you would basically get the list of data nodes that contain that data in replica or the original format, and whichever data node has the lowest latency from your location, it would basically fetch that fetch the data from that data node, and you'll get to read it from the client's end. So that was about it for how the HDFS architecture works. We will now look at the MapReduce workflow. So now we know how storage works in the HDFS. Now we will have a look at how processing works in our Hadoop ecosystem. So firstly, we have our databases. We can see that we have D1, D2 up until Dn, depending on how much data we have and how many data sources we are taking our information from. So D1 to Dn are basically the data blocks of an input source. So whenever we run a MapReduce operation, we're obviously taking some data from an input source, right? So that data inside of an HDFS, depending on its size, will be divided into blocks. So whenever the data is divided into blocks, depending on the block size configured into your HDFS, the first thing that happens in the MapReduce, as it says in the name, the mapping. So the mapping basically creates key value pairs out of that data. So the key elements are the ones which are accessed in order to access the data elements within that MapReduce operation. And this after the mapping is done at 100%, where all of the data is reduced down to key value pairs, then we move on to the reduction part. So all of the data that is present from the output of these mappers are then shuffled. So why does shuffling occur? Shuffling occurs in order to send all of the data with the same key values, with the same keys to the same reducers. So whenever there is a data with a particular key, the mapper would send it to one reducer and one reducer only, in order to maintain consistency whenever data aggregation occurs. So we will discuss how this works later on when we actually move on with our tutorial, when we actually execute our hands-on tutorial, to give you guys a clearer idea of how that is functioning. So after that is done, the reduction part happens. So data with the same keys is sent to one reducer. That is where the shuffling part occurs, and the reducer basically aggregates all of our key value pairs to give us our final output. Now this could be a word count program, this could be a mathematical evaluation where the same keys are being evaluated with an addition operation or a subtraction operation. It could basically be anything. The point of it is being implemented on extremely large data sets. And it is being implemented in a parallel format with this particular logic. So all of the mappers are running in parallel, and all of the reducers are running in parallel as well. And the mappers are running independently of each other, and the reducers are running independently of each other as well. Very drastically reducing the time complexity of the entire operation. So this is the final architecture, the final MapReduce workflow that we have. So now let us move on to the tutorial with the Hadoop ecosystem that we have. So we're going to be executing a word count program using MapReduce and actually taking the output from that word count program and creating a Hive table out of that output and actually performing a simple query on that table just to give you guys an idea of HiveQL as well. So let us begin without any further ado. So currently we are in our Hadoop virtual machine. So we have our Hadoop ecosystem already set up with Hadoop and Hive. So the first thing that we're going to do is create a folder in order to store our input file. So we'll type in mkdir and just create a folder. We'll call this folder YT for YouTube because we're broadcasting this session on YouTube, and press enter. So we've just created our folder YT in the present working directory of our Hadoop file system. So the next thing we would like to do is basically look at an input file where the input file is hello YouTube. This is Intellipaat. Welcome to our assignment session here today. So this is the content of that file, and this file is saved, so it's created, and we'll simply open up our terminal and transfer this file from our Hadoop from our local file system to our Hadoop file system. So we'll simply use -put for that, and the first argument for this put is the file name, and we'll just cross check whether that's the file name, sample T capital X T small, and we'll just cross check again as capital T capital X T small. So we've taken that as the first argument, and the second argument is the folder that we just created inside our HDFS, which is YT. So this will upload our sample txt file to our YT folder within our HDFS when I press enter. So after I've pressed enter, it has successfully done that. We can just cross check this by typing Hadoop fs -ls just to type our folder name, which is YT. And within that, we can see that there is an 82-bit byte file, which is called sample txt. So the next step that we need to do is run our word count jar, which is already created. So this is a Java-based jar which houses our word count code. So we'll simply type in Hadoop jar and type in word count. So word count is present within our desktop directory, which I'll just show you in a moment. Desktop/word count .jar, and within the word count .jar we have the class name we calling word count. So this is the driver class name which houses our driver code for that particular program, and so after that is done, we can basically go ahead and actually give the input source directory our argument 0, which is our input source file, which is housed within YT. So we can simply type in YT, and then we will give our output directory. So wherever we want to store our output, we'll give that directory. We'll call this YTO. O stands for output here, and then we press enter. So as we can see, our MapReduce job has started. So the first thing that you will notice is the mapping will go up to 100%, and after it has gone to 100%, then the reduction will start. And we can see mapping is 100 and the reduction has started. So after the reduction ends, we can basically scroll down and look at the logs that have been generated. So we can see the bytes read are 123 bytes and the bytes written are 103. So we can be sure that our output has been created. So how to check the word count output? Simply type in Hadoop fs -ls and then the output directory that we used. In our case, we used YTO. So when we type in that, we will get our output files inside the output folder that we used. So the indicative of success, there is a 0 byte file which indicates success of this particular operation, and there's a part 0 file which actually houses our output. Now the reason this is part 0 is because it doesn't exceed the block size of the HDFS configuration that I have. It is only 103 bytes and the block size of HDFS is usually 128 MBs, so it doesn't exceed that. So firstly we will now look at the contents of this before we actually move on to Hive. So type in -cat and then simply type in part 50. So actually first we need to type the YTO/part 50 and press enter. So we now have the contents that are present within our text file. So as we can see, hello, this YouTube assignment here in Intellipaat. So it's also in a particular order where all of the words are only occurring once. So if you just look at this again, no words here occur twice. So that is why all of the words are occurring only once. And if we simply open up our terminal again, we can open up our Hive shell as well. So simply type in Hive for that. First I'll clear the screen, and after I've cleared the screen, I'll type in Hive. So we start Hive shell. So we've successfully initiated our Hive shell. Firstly, we'll create a database within our Hive. We'll call this YT. We successfully created a database which is YT, and then we will use this database by typing use YT. So this is simple SQL commands. So big data is not that difficult if you know simple SQL. To use Hive, you can basically use it with simple MySQL knowledge as well. So simply type in create table YT, and the YT could be any name that you want. And after you've done that, simply type in the data types from your particular output that you may have. In my case, we have a string value, which is word, and word could be any column name that you would desire. In my case, I'm using word, and the second column name I'm using count, which is represented by an integer data type. So if you're familiar with SQL, you would understand this as well. So after that is done, simply type in row format delimited fields terminated by, and then given the delimiter that you're actually using. In my case, the delimiter that we're using is tabular D, which is representative of space. So if you would remember, if you would rewind back to where we actually showed the output from our HDFS, from our MapReduce job, we saw that the words and the numbers were separated by spaces. So they were not separated by commas, they were separated by spaces. So by using \t, we're actually using those spaces as delimiters so that we can actually divide those two data fields with a column. And after that, we're using the location of our output directory, which was /user/training/YTO. It could simply be written as YTO, but I'm using the absolute directory for this, just to make it clear that you can use that as well. And after that is done, simply press an enter. And you would create your table. So if we just look at the table and type in select asterisk from YT and semicolon and press enter, we would get all of our value in a tabular format as well. So this is a table. This is an SQL table. So we can basically now perform some structured queries on this as well. So before this, what you saw was a text file that just housed particular data divided by a space, but now we've converted this successfully into an SQL table. So this is a completely structured data format now. So that was about it with the querying of data after actually receiving the data from MapReduce. So this is how the ecosystem works together in conjunction. You can basically take data from anywhere and use various tools present within your Hadoop ecosystem to analyze that data in every way. So you can do this with Pig as well. You can do this with Spark as well. You can do something far greater with Spark. You can do something else with Pig. Everything has their own perks basically. So yeah, that was it for the tutorial that we had with our Hadoop ecosystem. So with the tutorial done, we are now at the further learning section of our session here today. So as we can see, there is a quote: an investment in knowledge always pays the best interest. So you can learn all of this from blogs or our YouTube channel. But if you're actually looking to specialize in this particular domain, which is the field of big data analytics or big data in general, you need to learn this particular technology in a much more organized and structured format. So for that, you can actually go ahead and opt for a course. Now there are a lot of courses online, but we'll just run you through the courses that we provide for big data analytics on Intellipaat.com to give you an idea. And if you're genuinely interested, you can maybe look into it or just maybe ask our course advisors about it. So just let me give you a rundown of the courses that we have. Simply log on to Intellipaat.com. So once you're on the website, simply type in Hadoop ecosystem. Just type in that. Press enter. So you get a lot of results right now. So one of the courses that you can absolutely opt for is the Big Data Hadoop Developer Certification Training Program that we have over here. If you're purely wanting to get into a developer role, so the specialities of this course, we can look into that, the key features that we have. 30 hours instructor-led training, 30 hours self-paced videos. So you basically get live classes taken by industry professionals, years and years of experience. You can get those classes and they would be live. So if you have any doubts throughout the class, if you're taking a class and you have a doubt, you can basically ask the instructor live using the online medium of communication that you have, and the instructor would resolve your doubt live for you on the spot. And if the instructor is going too fast or too slow and you need some self-paced content in order to get in line with the instructor or get ahead of the instructor in that regard and actually do a little bit of studying on your own, you can basically look into the self-paced videos as well. And if you have any doubts that accumulate from the self-paced videos, you can ask those doubts from the instructor. And aside from that, what you will do on your own is 60 hours worth of project work and hands-on. So hands-on and project work is really important when you're learning any technology, because that is the actual thing that gives you experience. You can look at videos of people coding, but unless you actually try it on your own, you will not be able to retain the amount of knowledge and amount of experience essentially in that particular technology unless you go ahead and do it on your own. So that is included in our course as well. A lot of project work and exercises will be given to you and be actually checked by the Intellipaat team to basically guide you in the right direction. And then after you've completed the course, you get certification and job assistance. So the certification is the obvious thing that happens. You complete the course, you get a certification. But not only that, we actually forward your resumes and career qualifications to potential employers as well. So if you actually do good on the interview, if you actually do good based on the interview, you will actually get a job out of this as well. So we cannot absolutely guarantee you a job, but we can certainly guarantee you a job assistance. And there is a flexible schedule. So if your professional schedule does not line up sometimes with the instructor schedule, you can basically ask yourselves to be basically added to another batch without actually missing out on the live experience. And if you actually miss a class, you can get that class in a self-paced video as well, because the classes are recorded. So other than that, we provide with lifetime free upgrades. So if there is a significant change in technology which changes significant features of this particular technology that you're learning, there is a lifetime free upgrade, and the technology is upgraded and you would get that new content for absolutely free. And other than that, there's 24/7 lifetime support and access. So if you're facing any sort of a doubt, any sort of a technical or any other doubt in that regard, the Intellipaat team is there for you 24/7. One of the services that we provide in our organization. And if we go over and look at what we will actually learn if we actually take this course, we have the Hadoop architecture, the Hadoop basics, the HDFS, Hadoop MapReduce functionalities, how to deploy Hadoop clusters and MapReduce programs, and Yarn programs, big data analytics using Hive, Big and Yarn. So some of the Hadoop ecosystem programs, MapReduce in Edge base, Spark, understanding the RDD in Apache Spark, job scheduling using Uzi, and you can also prepare for the Cloudera Spark and Hadoop developer certification. So there's a certification program by Cloudera, and this course actually prepares you for it in the field of big data analytics. So you can take this course if you're a software developer, specialist in analytics from business intelligence or ETL backgrounds. And if you're already a Hadoop developer, architect, or a testing personnel. So the content. So if you're actually looking to dwell into the course content and have a look at it in detail, you can head over to the course content and look at what we actually teach in each of our modules. So yeah, you can just simply expand this and look at what are the contents of this. So it's not just only this course, you'll get a lot of courses as well other than this. You just simply back it up for a second, you'll get Apache Spark, Scala, and Storm training. So if you're only looking to dwell into Apache Spark, you can basically open up Apache Spark as well. And if you're looking for the Python and Spark combination, which is the trend for today, hot topic for today, if you're coming from a data science background, you can simply opt for the PySpark training as well. If you simply type in Hadoop, you will get that as well. A lot of courses for Hadoop as well. So the most popular that we have is the Big Data Hadoop certification training. So this is the most extensive course that we provide in this regard. So you can simply open up that and look at it as well. So that is about it for the session. But before we go, we actually have a course offer for you. So if you are genuinely interested in any of the courses that we provide at Intellipaat.com, if you use the coupon code especially for our YouTube audiences here today, if you use the coupon code YouTube30, you will get a flat 30% discount on all of the courses that we provide, not just our Hadoop courses. So yeah, if you're looking to subscribe, be sure to use this coupon code and get a flat 30% discount. And with that out of the way, we are at the end of the session. So the contact details in order for you to contact any of our course advisors, if you're genuinely interested in the courses that we provide at Intellipaat, you can use the following contact details for that. This on your screen, and I'll see you again in the next session, which will be at 5 p.m. IST. So thank you and goodbye from Intellipaat.